So we're going to try to finish chapter 5 today. I don't know if we'll always succeed, but we're going to try. And we need to start that by talking about spontaneous combustion processes. So most of the combustion processes that we think about are in the normal combustion kind of. We have to introduce some sort of fire starter. We have to introduce a flame. We have to introduce some sort of electrical shock. Something induces the reaction and gets it to start and catch on fire. But there are certain substances that, as they are heated, they can actually kind of just go undetected in terms of their combustion until they generate enough heat from their combustion that their own heat from their degradation provides enough energy to start the fire. That's what we refer to when we call something a spontaneous combustion. We haven't introduced any external source of flame, of electrical spark. But as we just gradually heated up the substance, and as it has gone through its own degradation process, the energy that is created as part of its own self-combustion heats itself and eventually starts to provide enough energy to get the whole thing to go up, to get the whole thing to ignite on its own. So this is, as you might expect, a relatively rare process. It's not very common to basically just heat something up to the point where it just ignites on its own. Auto ignition temperatures for things are usually quite high. And so it's far more easy to just introduce a flame, set it up, allow it to arc a spark into it, something like that. Now that we're on the subject of fires, we have to understand there are five different classes of fire. 5 different classes of fire are given letter designations, and they kind of fall into general categories. So your class A fire, this would be your ordinary materials. Good way of thinking about it is you think about A for ash. Anything that burns and leaves behind an ashy residue, that is the subject of a class A fire. So we're talking about things like building materials. We're talking about things like wood, clothing, paper goods. Pretty much almost anything that you can find in your house is going to be in a class A fire kind of designation. For your class B fires, you're talking primarily about liquids, flammable and combustible liquids. So here we're talking about things like oil, propane, petroleum, gasoline, diesel fuel. So if we can burn it and use it for things like home heating, powering your car, it's a class B material. Class C materials are electrical. So any kind of device that has electrical equipment that could potentially spark, That is a Class C fire. So electrical fires fit into that category. Things like electric toaster ovens, toasters, electrical wiring in houses. Class D fires are for specifically combustible metals. So this is one that you probably more than most are familiar with just because of what you do and what you're learning. But we're talking about metal shavings, magnesium, aluminum, calcium, all of the alkali metals in group 1. They're all combustible metals. They're all things that if we put them into the right circumstances, they will ignite, and ignite usually with a good bit of heat and light. And then finally, K. Class K, you think of Class K for kitchen fires. What we're talking about there specifically are usually things like animal fat, vegetable oil. Anyone ever work in a fast food restaurant or in a commercial kitchen? I did too. I actually remember the training video that we had to watch for the deep fryers. I worked at Wendy's for 2 years. And yeah, the training that you had to go through, if a fire were to ever start in one of the fryers, here's what you do. Yeah, I can imagine. But that's your Class K. So again, vegetable and animal fats, cooking oils, those are kind of the most common things. And so those are the 5 designations. Now, what we're going to get into now is talking about, kind of what the fire process looks like. And there are a couple of ways to address that, called the fire triangle and the fire tetrahedron. And this will kind of move us in the direction to talking about how to stop those fires, because fire extinguishing media, whether they're fire extinguishers or foam systems, or in the case of Tristan trying to burn down the KFC, there's usually an overhead system in commercial kitchens that will shoot off a fire extinguishing agent automatically. And each of those systems, regardless of what they are, aim at breaking either one of the legs of the fire triangle or one of the parts of the flame tetrahedron. And if you can break either one of those and stop one of those components from continuing or occurring, that effectively puts out the fire. So for the fire triangle, what we see in the fire triangle are the 3 things that we need for combustion reaction. We need something to burn. That's the fuel. We need oxygen to react with that fuel to continue to combust it. And we need sufficient heat to bring the 2 together at the proper energy to get that reaction to go and to keep it going. Now, the only difference between the fire triangle and the fire tetrahedron is the concept of this idea of a free radical. Free radicals You hear them sometimes talked about, especially if you listen closely to like cosmetic commercials, or things that have to do with like your skin. Free radicals are talked about as one of the things that make you look older. Don't know exactly the truth of that particular statement, but what a free radical is we have a molecule or an atom with an unpaired electron in it. And we know from our discussions in chapter 4 that substances that have unpaired electrons don't stay unpaired for very long. So the presence of that radical is what allows a reaction to continue to keep on. Sometimes you'll see this referred to as like a chain reaction or a chain of propagation. And what that really means is, so long as we've got those radicals present, we're going to have a constant source of reactive substances to react. And that's going to keep it going. So we look at the fire triangle, you can see this is pretty easy. If I knock out the oxygen, heat and fuel alone are not enough to start a fire or to keep the fire going. If I take away the heat source, simply having fuel and oxygen present at the same time isn't enough to get the reaction going or to keep it going. Look out in that parking lot right now. You got a bunch of cars with a whole bunch of fuel in them, surrounded by an oxygen-rich atmosphere. None of them are on fire right now. We're lacking a certain component. We're lacking that heat. The fire tetrahedron, again, we're adding this free radical piece to it, but the idea is kind of the same. Knock out any one of these legs, free radicals aren't going to be nearly as readily available. Knock out any one of these legs, fire's going to go out. So let's talk about how we can actually remove these different aspects. So we're going to talk and start with probably what we would consider the most common fire extinguishing agent. That is water. Now, water is probably best used on those Class A fires. So again, the reason we associate it with firefighting is because the majority of the time when we see firefighting taking place, it's taking place at a house, in a forest. It's stuff that's all common materials. And so because of that, we see that water is really effective, or at least best effective, on Class A fires. And the thing about water is, especially with the way that we have our municipal system set up, water is always available for use. Now, water can be effective on flammable liquids, but there are some really important conditions that have to be met. And this is usually where we run into problems, because most of the time the flammable liquids don't qualify under these categories. First of all, water can be an effective firefighting tool if it is immiscible, meaning it does not dissolve in the burning liquid, and its density is such that it floats on the surface of the substance. Again, that's where we run into a lot of problems. Most of the burning fuels that we're talking about have really low densities. And so water isn't going to float on them. It's more dense. It's going to sink. So gasoline. You have a gasoline fire, water's not going to be the most effective tool for it. You can use it, certainly, but it's a good chance it's going to spread stuff out more than it's going to help you. And the reason why, it doesn't dissolve, and the water is just going to go underneath it. And so as the water goes underneath it, you can just float on top of the water and go wherever it wants. The other place where it's effective is if it is soluble in the burning fuel. Any of you guys that might follow like car racing, Indy cars, Formula One, most of those engines run on low molecule alcohols, methanol, ethanol, high octane fuels. But the thing about all of them, they're all soluble in water. So if a fire breaks out in an Indy car, first thing that they usually do is go out there and pour water, lower the temperature of everything. And since it's all soluble, it's a pretty good means of fighting the fire. We can also see it when the moisture content of the air, so if the air is particularly humid, water can be effective in that regard because it can draw moisture, it can draw heat out of the fire and help to lower the overall temperature, which can take away some of that energy leg of the triangle. Problem with it is that water is, we use it in a house, it's really damaging. You're pouring gallons upon gallons upon gallons of water to fight a fire, and those gallons upon gallons upon gallons end up still in the house after the fire's put out. Because it is fluid, its vaporization characteristics can be kind of minimized. And one of the things that we really want, we can pull the most energy away if we can get the water to vaporize, because the heat of vaporization for water is large, huge. But because of its fluidity, because of the way that it moves, getting it to the vaporization stage is actually pretty hard. And so again, as a result, most of the water stays in the liquid phase and it just seeps into whatever material is left over once the fire is put out. Days like today, days like we've had in the past few days, cold temperatures can lead to freezing conditions, which again, if it freezes, we can't use it. And if it's super cold, it's going to be even harder to get it to vaporize. Because of its density, we can't use it for most burning liquids. It's not going to float on top, it's going to sink to the bottom. Again, if it sinks to the bottom, that actually just provides a vehicle for that burning fuel to go somewhere else. Water and electronics do not work well. Anyone with a cell phone will tell you that much. And water is often a reactant if we have burning metals. So a lot of the metals that burn also react violently with water. So really, our use for water as a fire extinguisher is extremely limited. Now, sometimes it is the only and best option we have, but it still has a very limited window of effectiveness. And we can't say that it does its job without causing some kind of damage. So how can we use water? Well, it depends on what the circumstances are. There are small handheld fire extinguishers that use water as its fire extinguishing agent, either as just like a spray, just like a garden hose, or with a mister on it. And what the advantage of the mister is it helps promote that vaporization. And that vaporization would allow the fire to actually be put out faster by taking more heat away more quickly. For larger fires, well, that's what Jacob can tell us all about. We're talking about, your traditional large fire hose, or we're talking about things like fixed extinguishing systems where we have a permanent nozzle or we have sprinklers that are used in larger spaces. Now, as I said, if the option exists to discharge the water as a mist, that is actually a preferable option, because from an efficiency standpoint, water is the most effective when it completely is vaporized. So when we go from water in the liquid state to water in the gas phase, its ability to draw out heat is way better. Now, obviously, the problem that we have here is that if you're dealing with something on the larger scale, you're not going to create nearly enough mist to negate the energy that is coming from the fuel burning. But the big play here is all about surface area. Creating a mist as opposed to a stream of water is going to make the vaporization more likely, because we're getting a greater surface area. We're getting more water molecules exposed to the heat to get converted to the vapor than we would have otherwise. Again, the problem that we run into is that if we are dealing with something large scale, we can't produce nearly enough mist to start to reverse the flow of energy, which is really what we need to do. If our fire is producing 1 million BTUs of energy a minute, and our water is only taking away 500,000 of those BTUs, the fire is still growing. And we don't want that. We would want the opposite. We want to have 1 million BTUs being outputted, and we're taking away 1.5 million as we're starting to shrink down the fire, trying to knock out the heat. Now, another version that we can get into, foams. Foams have become increasingly more useful and more common in their use over the past 15, 20 years. This one in particular, the aqueous film forming foam, what happens there is the water gets sealed into a gel, and the gel is able to kind of sit over top of the burning material. And what we get there is two things happening at the same time. We get a method to try to block the fire's access to oxygen. So we're trying to knock out one of that leg of the triangle, and we still have the water trapped inside, which is able to take away the heat. So we're kind of knocking at it from two sides. But as you can see, this is a temporary kind of fix. Hopefully this is enough to get things slowed down and potentially extinguished. But if you've got something that's raging on for a long period of time, it does have somewhat of a shelf life. There's another kind of film. This one's an alcohol resistant foam. We can see this one used more in Class B situations. And this one is best for small fires. Again, with larger fires, this isn't as good, but it does allow us to use a water-based substance, this water-based foam, to put out fires other than Class A fires. There's another type of foam called a protein foam. This one's kind of interesting. We see it prepared from some sort of natural based protein material. So it can come from things like soybeans, plant-based. It can come from animal-based sources like fish meal or horn and hoof meal or feather meal. By definition, it is 3 to 6% weight of the protein plus some sort of stabilizer. And the idea is to create a more permanent kind of barrier. Again, the whole point of foaming is we're trying to blanket the fuel source with something that's not flammable to block its access to oxygen. So that's what foams do. Now, aqueous foams can also bring on kind of some of the water properties as well in terms of heat reduction. But again, the primary focus of a foam is separation between the fuel and oxygen. That's what its purpose is. Pyrocool is another kind of foam. One of the proposed advantages to pyrocool is that it is supposed to be environmentally benign. Again, appropriate term there is benign. Calling something environmentally safe has a lot of different rules attached to it. But being environmentally benign basically just means it at worst doesn't cause any harm. So what does it do? It's a foam. So like all foams, its primary purpose is separating the fuel and the oxygen. How it works in particular is it reacts on the surface of the fuel. And what it can do in that case is it basically works at the interface between either the liquid agent inside the foam and the liquid that is burning, or the liquid agent inside the foam and the solid that is burning. And so trying to get those to interact with each other more, and basically creating a competition reaction. So instead of the fuel reacting with oxygen, the fuel is interacting with the fire extinguishing media. And since we're taking away the source of oxygen, and sometimes taking away a little bit of the heat in the process, the fire starts to subside, the fire starts to go out. All right, so that's water and all the water derivative kinds of substances. Let's talk about another kind of fire extinguishing media. Another common one, carbon dioxide. Now, carbon dioxide fire extinguishers, we can always tell what they look like. So a common carbon dioxide fire extinguisher should be red in color, and it will have a black nozzle on it, and the black nozzle will have a funnel-like opening at the end. And the reason for that funnel-like opening is for the dispersion of that carbon dioxide gas to help push it out in multiple directions. So this is especially effective for Class B and for Class C fires. We generally don't see them for Class A fires. And the reason we don't see them used for Class A fires very often is because, well, they're not that good at it. And if we think about what Class A fires are, again, we're talking about materials that are ashy as they burn. Having a large jet of high pressure gas going into a ashy substance doesn't often put it out. In fact, we can just help blow that stuff around. So one of two things happens. We either blow out something that is still smoldering and push it farther away, which can, depending upon its temperature and what else is around, could start a new fire over there. Or even if it doesn't start a new fire, it makes a gigantic mess, as all of that uncombusted material is basically just going to get pushed out everywhere. So we generally don't see them used for Class A fires. We definitely don't see them used for Class D or Class K. They're just not effective. Now, how they work is two things. First of all, because they are heavier than air, when we spray them out, it's going to go down and spread out in a downward fashion. And its primary purpose isn't for heat reduction like water was. It's for putting a barrier between the burning material and the oxygen in the air. Since it is more dense than oxygen, if you've got a layer of carbon dioxide around your fuel, it's a lot harder for the oxygen to get in there to burn it. And so that's where carbon dioxide is the most effective. Where we see it most often is in the portable handheld fire extinguishers. Now, it's also possible to see it in a fixed system using storage tanks and nozzles very similar to sprinklers for larger scale kinds of operations. So where I've seen those have been primarily in things like lacquering rooms, finishing stations, where you might have a high concentration of volatile materials in a confined space, and a simple spark could, or something bad could just end up causing the whole thing to ignite. That actually happened. To my father. My father worked at a place once where they had a lacquer room, and a fire started in the lacquer room, and the fixed extinguishing system actually failed, burned down the entire building. It was 100+ year old factory in my hometown, gone within a couple of hours. Because once it spread out, there was not very much they could do about it. So we often think of carbon dioxide as kind of a, that image of just a small fire extinguisher. Again, the difference between that fire extinguisher and some others is that fluted nozzle at the end to spread out the carbon dioxide. But there are some other applications as well, where we can use it kind of similar to a sprinkler system, but with class B and C kinds of materials in mind. There are some foaming systems that do use carbon dioxide. So we can trap carbon dioxide into some of the bubbles of chemical foams. Again, the purpose of the foam is barrier, creating a barrier between the carbon dioxide or between the fuel and the oxygen. Often these foaming systems are two solution systems. So basically, you've got starting materials in separate tanks, and then they are combined to create the foam in the moment. So how that works, the aluminum sulfate and the sodium bicarbonate are in different solutions. When they are mixed together, they will form this foam that also forms carbon dioxide as a byproduct. And so the whole thing comes out as one. All right, some other kinds of common extinguishers. We have the halons. Halons are substances that are not flammable, and we have to have both of these criteria met. We either have to have 1 or 2 carbon atoms and between 4 and 6 halogen atoms. So what we're talking about here are compounds that are either carbon with 4 halogens, or if I have a 2 carbon system, then there are 6 halogens. So we are talking about molecules that are exclusively carbon and halogen. There is no hydrogen, there is no oxygen, there is nothing else in these materials other than the carbon and the halogens. These substances are dense, much more dense than air. And what they do is they will produce free radicals. Now you may be saying, well, isn't that one of the things that we're supposed to look for? Isn't that one of the things that can continue a fire going? Yes, if we were talking about a flammable material. But we're talking about non-flammable materials here. So the creation of those free radicals, what do? They attach to the other free radicals that the fire is producing, and they stop the chain reaction. So this is kind of a counterbalance measure. We take out one to stop the other. We create non-flammable free radicals to react with the flammable ones and create a non-flammable substance as a result. Now, this is kind of a cool concept, and it's very effective against Class A, B, and C fires. Problem is this. There is a potential link between halons and the depletion of the ozone layer. When those free radical substances, when those halogenated compounds make their way up into the atmosphere, as most gases do eventually, those free radicals can react with that upper atmosphere ozone and turn it into oxygen. Since ozone in the upper atmosphere is responsible for blocking UV light and a lot of other stuff from entering the atmosphere and help keeping us somewhat safe, halons were largely banned starting in 1994 and going out to 2001. They have been banned for everything considered a non-essential use. Now, government speak being what it is, the definition of essential use has some degrees of freedom to it, I would say. There are still a number of firefighting companies that utilize halons for various reasons. But their use is not nearly as widespread as it once was. We started to look here at the dry chemical fire extinguishing agents, and we noted that they kind of fell into categories based upon what kinds of fires they could put out. So your classic bicarbonate substances were good for B fires and C fires, but not so great for A. Your Class D fires have their own kind of dry chemical fire extinguisher. We'll talk about those more in a second. Your ADC fire, this is kind of the classic fire extinguisher that you have in your home. You go out into any of our emergency response stations here in the building. All of those have ADC fire extinguishers in them. They're dry chemical agents, so we're talking about solid substances. But the big downside to them, and this is why you have to be careful and make sure that you're only using them for the intended purpose, is that they leave a really messy residue. I promised you at the end of last lecture, I'd tell you a story to this end. And the main idea there is when I was in college, I was a sophomore, and I was staying in the upper class dormitory, and there were a bunch of athletes that lived on my floor. It was always nice to have them around because they usually had interesting stories and they were kind of college characters themselves. Well, they had just come back from a conference championship and they had won, which was fantastic. And so they'd been partying in the room and they were pretty loaded. And all of a sudden, one got the bright idea that they needed to take the party out of the room. And so they took the fire extinguishers that were at the ends of the hall, and they decided to just start spraying them everywhere, all up and down the hall. Well, this tripped the fire alarm in our dorm, and we all were sent outside in February in northern Pennsylvania. So it was about 10 degrees outside. It was about 2 in the morning on a Saturday. And we're all sitting outside and we're all waiting while they try to figure out what tripped the fire alarm. And then the resident assistants and the people involved go to our floor. And they see this big fine mist of powder just hanging out. I was allowed to go back to my room for 5 hours. Why 5 hours? Because that's how long it took the dust to settle so that we weren't breathing in the monoammonium phosphate as we were trying to walk back to our room. Now, in the emergency situation, because when we opened the door, we just saw this cloud of what looked like smoke, we actually thought the building was on fire. Because in an emergency situation, you really don't think about the difference between an ash fire and what is just a yellow cloud of powder dust. It looked kind of the same, especially bleary-eyed at 2 in the morning. But yeah, 5 hours. Everybody else had to go back to the rooms, but because all the mess was on our floor, it took 5 hours for us to get back to our room. And when we did go back, it was like footprints in the snow. You could see all the little cracks going from the doorway to each one of the rooms because of the powder residue that was left behind. It took forever to clean up too. It was expensive. So I went to college at Westminster College in Pennsylvania. It's a Division III school. So that was the other fun thing about that particular thing, is because there were only about 1,500 campus students, period. Everybody knew everybody, and everybody knew the story by the time we woke up the next morning. There's also a whole lot of discussion about who to blame and how it's going to be paid for, because just refilling the fire extinguishers is going to be expensive enough. Cleaning up all the residue was going to require several man hours, and they'd figure out who's going to pay for that. So that was not as much fun. I always remember that story, and this bit about that residue is no joke. One of the reasons why you need to make sure that if you're going to use a dry chemical fire extinguisher, make sure you actually need to use it. It's not a toy, and it leaves a heck of a mess when it does, even if you're using it properly. Now, if you're using it properly, you don't care about the mess. You put out the fire. But if you aren't, then it's just a big, heavy mess, and you don't want to breathe in that stuff. Now, the BC fire extinguishers, the ones that are bicarbonate based, the way that these work is you get a couple of things. When they are heated, bicarbonate substances will decompose. And what they will decompose into are water and carbon dioxide. Carbon dioxide obviously works as a barrier. The water is actually somewhat ineffective because it's already in the vaporized phase. So its ability to absorb heat isn't that great. Some of the sodium atoms are able to react to form liquid water. That liquid water can be somewhat effective, but the real thing behind the BC fire extinguisher is its ability to create carbon dioxide and put in that barrier between the fuel and the oxygen because of the density of that carbon dioxide. So that's how a BC extinguisher works. And this would be the same for any bicarbonate material. It is one of the reasons, if you have a small kitchen fire, you know, like say you're frying up some hamburgers in a skillet and it just starts to kind of flame out of control, but you can pour baking soda on it. You pour baking soda on it. Baking soda is sodium bicarbonate, and so it basically acts in the same kind of manner as a BC fire extinguisher. Ruins your food, but if it was engulfed in flame, it was doing it already. So that's a scenario where you can use what's in your kitchen or what should be in your kitchen already to take care of small issues like that. ABC fire extinguishers, again, those are monoammonium phosphate. We see them primarily for home use, as well as some minor industrial uses. And certainly things like building fires, things like general safety action plans would have ABC fire extinguishers present at least on every floor in a building, if not in multiple places on each floor. And for the same kind of reason. Now, one thing I deliberately, they are better on Class A fires than other dry chemical agents. So we will see that they will be dropped on forest fires from above. And that aerial action will help to do the same kinds of things, absorb heat, blanket the substance from interacting with oxygen, and so on. Now, how they work primarily is just like the bicarbonate, they decompose on heating. So that term endothermic there is a scientific way of saying that it absorbs heat. By absorbing that heat, it's taking heat away from the chemical reaction, it's lowering the temperature, and eventually, hopefully, lowering it down below the ignition temperature. The other part is that the ammonium ion will generate ammonia on its decomposition. And ammonia is a particularly reactive gas that can create free radicals. And we talked about free radicals on Friday, on Wednesday. The idea that you have a substance, free radicals are necessary to generate the chain reaction to keep the fire going. Well, if we have an alternative source of free radicals other than the combustible material, that will stop the propagation of that chain reaction. We're introducing something that is not flammable to react with the flammable stuff, which will make the flammable stuff non-flammable at the same time. As with all dry chemical agents, they leave a mess. They're not clean agents. They're not going to leave behind no residue. The carbon dioxide, you know, what we saw for BC fires, doesn't leave behind much of a residue. But the dry chemical agents, they certainly will. All right, two more to talk about. Class D fires. So again, Class D fires are metal fires. And what we see in dry chemical Class D extinguishers is either powdered graphite, which you know better as pencil lead, or sodium chloride, table salt. Those dry chemicals are then mixed with some kind of compressed gas that is not flammable, something like a nitrogen or you know, some sort of noble gas, so probably nitrogen is most common. If you have it in an actual fire extinguisher, you'll have the compressed gas in it. It'll be discharged by a stream, just like you see with the ABC fire extinguishers. If you don't have those, then you can use a tube or a shovel. You can basically just kind of keep dry chemical agent onto the metal fire and it'll work it out. The reason we can't use water with these is because the substances that are formed, especially the graphite, are metallic carbides. Metallic carbides are generally stable substances, but if you put them in the presence of water, those carbides will decompose and react very quickly and produce a series of flammable gases based upon what the carbide is. And you'll see this when we do the flammable solids lab. You'll do a burning ice experiment where you'll take a carbide and react it with ice, and the whole purpose of the ice slow the reaction down. So you'll take the ice and you'll actually create these small pockets of acetylene that get generated from the reaction of the carbide with the water. So some carbides will form acetylene, some will form methane, some will form other things as well. Got to be really careful with them. That's why if you use graphite method, which is the more effective one, can't have water anywhere near. It's just going to raise up the whole flammable reaction again. Last kind of fire extinguisher is the Class K fire extinguisher. What we have in those is usually some combination of potassium substance mixed with water. And what the potassium substance is going to do is, in being mixed with the water, create a wet chemical agent. And the wet chemical agent is going to work through something called a saponification reaction. Saponification reactions are soap making reactions. So we heard a story on Friday about a deep fryer catching on fire in a restaurant. Now, in those deep fryers, depending upon what food establishment you're talking about, they either will contain vegetable oil like soybean oil, vegetable oil, canola oil, something along those lines, or in rarer cases, it contains something like tallow, beef fat, lard, pig fat, some sort of animal byproduct. So which one they do depends on what they're going for as far as taste and flavor and all that stuff are concerned. But nonetheless, that is fact in this particular circumstance. And when that agent gets sprayed onto it, the wet chemical agent is going to do this. It's going to create a saponification reaction. That wet chemical agent is going to react with the hot boiling fat and turn that hot boiling fat into soap. And that process is going to absorb tons of heat, and the layer of soap is going to block out the oxygen. That's basically what happens. Now, initially, when you see that sprayed on, it's going to look like the fire gets a lot bigger initially. That's just because the water in there is kind of reacting first. Anyone knows to take water to a hot oil, it just bursts up in flames because the water forms steam, and the steam just causes the more oil to evaporate, and it just goes up in a big flame. So initially you see that, but very quickly those chemical agents go to work, the fire's out in less than 30 seconds, usually. Now these are done within a fixed system. That fixed system, the series of nozzles like sprinklers over top of the deep fryers, which is why deep fryers are always in one position inside of any kind of restaurant. You don't see them move around a whole lot because you need that firefighting system there in case something goes bad. As we've mentioned with a number of these, they do leave a mess. It takes a long time to clean them up. But since they are in a fixed system, very rare that they ever actually get used, turned on. As I mentioned before, my first 2 years of college, I worked weekends at Wendy's to try to just pay the bills, give me a little spending money. And they gave us the training video, as they should, that talked about this particular system. And never actually saw it in action. Saw a lot of other things those 2 years I worked there. A lot of other things. But that wasn't one of them. When things are going well, when people are working properly and safely, it shouldn't happen. Sometimes accidents do, especially if you're dealing with a whole bunch of frozen stuff and hot oil. It can happen. But generally speaking, it doesn't. And with good training, you know exactly what to do to get to that point where it's a massive get everybody out of their kind of situation. So that is the end of chapter 5.